Hello. I think this is a very interesting problem, which is asking which is the most basic atom. I think most students would rather have the question, what's the most acidic proton? Because they could use a pKa table to look up which proton has the lower pKa. In terms of looking at the most basic atom, though, we have to reverse our thought and we have to try to analyze which atom is more likely to grab a proton. Because I teach my class, bases use a lone pair to grab a proton. In this molecule, there isn't any very acidic hydrogen, right? Any hydrogen connected to carbon is not very acidic. So caffeine acts more like a base in water and obviously under acidic solutions. Now, there are a couple things that we can eliminate, a couple sites or atoms we can eliminate. First of all, nitrogen is more basic typically than oxygen, right? Because oxygen is very electronegative. Typically, it doesn't want to grab a proton to become positive. So I have our 4 nitrogens and the lone pairs of those 4 nitrogens written out for caffeine. When you have, let's eliminate a couple more. When you have a nitrogen next to a C double bond oxygen, something like this, okay, that is actually less basic than a nitrogen with no C double bond oxygen next to it. Why? Well, first of all, this is called an amide. So amides are less basic than amines. This one here is an amine, a nitrogen with 3 single bonds but no carbon-oxygen double bond. Amides are less basic because the lone pair that you would think is used to grab the proton is occupied by resonance with this group here. So let me draw it here. Now, resonance is a stabilizing effect. So if that amide is very stable, it doesn't want to react. It doesn't want to be a base. It doesn't want to change. And my reasoning is that the lone pair is occupied by resonance. We have to be very careful how we use resonance. This is telling me that that lone pair is not available. Now, later on in this video, we're going to look at resonance, and it will be a good thing because resonance is stabilizing the conjugate acid. But again, I'm not looking at the conjugate acid yet. I'm looking at these lone pairs and seeing which one has a good chance of grabbing a proton. So we are eliminating this nitrogen. That's called an amide. And we're eliminating this nitrogen. It has actually 2 places to have resonance, and that's actually called an imide. So let me write that down. And we are eliminating these. These are not very basic. Amide. And yeah, there's a special name if there are 2 carbon-oxygen double bonds on the sides of the nitrogen. That's called an imide. I-M-I-D-E. We are eliminating those. Again, resonance is telling us the lone pair is not very available. Now, like I said, I warned you that we are going to look at resonance and it will be a good thing. Let me show you why. The first nitrogen that I'm going to inspect is this one here. Okay? So if this is the base, we are looking at the stability of the conjugate acid. And this is our first conjugate acid. Let me move this a little bit. Okay, it is a big molecule, relatively big. Let me see how I can shorthand this. There we go. Nothing is happening on the left because these 2 nitrogens are not very basic. But I am pretending right now that this hydrogen got protonated, and I'm going to assess whether that is likely or not likely. Remember, that's what we're looking for. which nitrogen is more likely to grab the proton. Okay, so that is our first conjugate base. I'll write it here. And I am going to compare it to another conjugate base, and those are my two choices. Either the nitrogen pointed by the blue atom or the nitrogen pointed by the orange atom. Okay, I'll keep the color coding going. And now this is our second conjugate base that we have to figure out, is this likely to happen? Okay, the top nitrogen here stays the same. It's the bottom nitrogen that gets protonated. Okay. This again, the second conjugate acid. Now when we use resonance and we look for stability, right? Stability in these two cases is good because it tells us that this reaction or this reaction will happen. Whichever conjugate acid is more stable, that equilibrium is more likely to happen, or that reaction is more likely to happen. And so if this conjugate acid is more stable, that means this nitrogen is more basic. If this conjugate acid is more stable, it means this nitrogen is more basic. Okay, and so what trends are we going to use to figure out stability? Well, a lot of times it will be resonance. Right now, the positive charge is on the same atom, so we're not worried about their electronegativities or their size. But one has resonance and one does not. You may think for the first conjugate acid that this is a valid movement. Well, that's not good because it will result in this nitrogen not satisfying the octet, and this nitrogen not satisfying the octet. I suggest you don't draw it at home, the result, but I'm just going to put it in notes. Result leads to nitrogen, both nitrogens actually, not satisfying octet. Right now, this arrow is no good, and I can't think of a way to get a new resonance structure that will help stabilize this charge. Let's take a look at this conjugate acid. When in doubt, draw your lone pairs. So let me draw this lone pair. Okay, the nitrogens on the left, I'm not worried about. Right now, I'm thinking, is there any resonance that we could show? And look at this. If I shift this to make a pi bond there, I can shift the pi bond here to neutralize this nitrogen. So definitely the charge is going to move because now this nitrogen will be neutral. And the result is this. Okay, now this nitrogen on top has a double bond to the right. It becomes positive. That's great because I just proved that we can share the positive charge. And here, the nitrogen is now neutral. That's the good news. So here, resonance is used to benefit the molecule in the sense that, yeah, this is stabilized, meaning this arrow is more likely to happen than this, meaning the hydrogen or the proton is more likely to go on this nitrogen. That's my conclusion, is that this is more stable because of resonance. Hence, this is more likely to grab the proton. Or, if we use proper terminology, this is the more basic nitrogen or atom. More basic. Let's use most. It's the most basic atom, period. Most basic atom. That's our answer. And why? because its conjugate acid is stabilized by resonance, whereas the other possible conjugate acid is not stabilized. Right, when your product is stabilized, the reaction is more likely to happen, and this reaction is more likely to happen. Let me just finish this thought. Because its conjugate acid is more stable, and it was via resonance. Okay, that's a good half page showing which nitrogen is the most basic in caffeine. And I'm also happy that I'm able to show you the resonance and the mechanism arrows.